So now that we've learned a little bit about what these individual HVAC control logic blocks do, we can start combining them in different ways to build different HVAC sequences of operations, and that's what we're going to look at in this video. So let's start with this Economizer mixed air damper command sequence. So we see at the bottom we have this control loop, we have this additional sequence on the top that looks like it's part of the enable. So just to kind of ease into this, let's look at how we might build this particular sequence. So you'd start with what you want to control, which in this case is the mixed air temperature. And you'd compare that to some set point and then generate that error in the PID control block so that it can pass out its control signal to something like a mixed air damper command. On the top is where you have this enable sequence, and we can break that down. First we see this AND block, which is telling us that all of the conditions upstream of this block need to be met for it to pass a 1 and enable the PID loop. The first condition is this Economizer enable, which can be done a few different ways, but it's essentially being passed from some other control loop or signal that could be something like a system scheduler or something like a proof of supply fan status. Then we have this comparator sequence that's looking at the Economizer high limit lockout and comparing that to outside air temperature to determine if it's energy efficient to use outside air in the mixed air stream. Similarly, there's a third condition to look at the Economizer low limit set point to see if it's too cold to be using outside air. And at the bottom, there's an indication of what this loop should do and what command it should send when the PID loop is not enabled. We can add some annotations here to indicate where the pieces of hardware are and whether the control signal is analog or binary, but that's about it. That's really the process we would use to build these sequences. So there's a lot of details though that we can get necessarily hung up on. So these are both Economizer sequences of operation. Can you tell the difference? Well, it can be a little bit hard to see at first, but on the right here you see that we've introduced return air temperature, and that's become part of the enable sequence. So what we have, without getting into too much detail yet, is this outside air only version on the left and this outside air and return air version on the right. So we want to be able to pay attention to how our systems are put together, and if we're going to change them, understand where to introduce that change to get the sequence that we want. So we talked about CLDs or control logic diagrams as being this graphical representation of all our HVAC sequences, and that on design sheets they're going to look something like this. So we're going to talk about some of those control loops, and in this video we're going to look at some of the simpler or no reset ones, and in the next video we're going to do our second part where we're looking at some of the more complicated systems that can have their set points reset and what that means. So we'll start with a preheat coil. So this is a schematic that is something of a system diagram and indicates how these controllers and different variables are tied together. So the first thing that we can see is that we have this DDC controller being represented here, and we have input information being sent to it, like this preheat discharge air temperature, and an output command going from the controller to something like this preheat coil valve. So that can be represented here with this control loop, and we see that same input, the preheat discharge air temperature, as an analog signal coming from a piece of hardware like an averaging sensor, and we have this output, the preheat valve command, that is also related to the hardware and is leaving the controller and being sent to the valve command. So what do we have here? We're a little bit further downstream in the system. Can you see the control loop represented? Well, we have a number of other systems and components shown. So we have things like this filter, DP or differential pressure switch. We have this averaging sensor immediately at the discharge of the cooling coil that is specifically for a safety circuit. It's also being picked up by possibly a different controller. But the main thing that we have is this cooling coil temperature control loop, or the valve command sequence. Also note that we have some abbreviations and acronyms for things like whether or not the valve is normally closed or normally open, and whether the control signal is direct acting or reverse acting. Talked about that in the last video, but that's going to be important as we understand how valves may fail and what the implications may be. So here's that cooling coil control loop. Looks very similar to the preheat coil in terms of how you're comparing the set point to the actual input and how that passes a command off. The enable may be a little bit different, but it's going to be important to make sure that we're not having unnecessary simultaneous heating and cooling, and we have different enables between, say, our preheat valve and our cooling valve. So what do we have here? So we got one more coil that might possibly be included in our air handling unit, and we can see it here as this heating coil control loop. But really we just want to think generally about what this system is doing and what we're trying to accomplish with these sequence. So as we talked about in the air side system, be aware of the preheat coil and the different problems associated with that. What's the intent of this thing based on your climate and your minimum outside air you're bringing in and your return temperatures and when you run? Is it possible that you're going to see freezing conditions? Is your air stratified in a way that may risk that despite your mixed air temperatures? Also be aware of where you may have simultaneous heating and cooling, what parts of your system that may occur at. So we want to coordinate our enables and our set points that get passed. We want to be aware of what valves may fail and in what position. We want to have alarms when that happens so that somebody is notified or somebody's checking to see if you're simultaneous heating and cooling. And be aware of some things that are by design simultaneous heating and cooling, like VAV reheat, and how that can be mitigated. And part of that just involves thinking about whether our set points make sense, either at all in design conditions or in the rest of the year where you're operating possibly at some part load condition. As an example of what we mean by that, let's take a look at this chart where we have average outdoor air condition plotted against natural gas usage at a specific building. So what is this data telling us? Well, one of the things that you might notice is that there's these two patterns that emerge here. And if I told you that this was for a building that only used natural gas for space heating, that might be confusing, because you would expect that if this was filtered for occupied hours, and because you might expect, as we did, that as it gets colder, that there'd be a single pattern where your natural gas use would increase. So what we found with these patterns is that using the Outlook calendar for a large auditorium at the center of this building, when the space was occupied, we had much lower heating use. When the space was unoccupied, that's when we had this excessive reheat because we had a single supply air temperature, 52 degrees, that was being pushed through the air handling unit, that when there was no people or equipment or lighting to really act as the load that 55 degree air was expecting to see, the reheat needs to pick that up. So that was one of the effects of having this static set point that didn't make sense for the vast majority of the year and was manifesting as this additional reheat. So what do we have in this system? So once again, we're a little further down in the air handling unit, and we have the supply fan. So we might call this the supply duct static pressure control loop, because the fan, in this instance, is being ran off a supply air pressure sensor that's down in the distribution of the duct. So we see that SA-P being brought into a DDC controller that then pushes a start-stop command to the VFD as well as a speed command and takes in a status back to the controller. And this is what that pressure input to the PID loop would look like, and then the supply fan command going out. So a few thoughts on the duct static pressure sensor in particular. So you want to see this thing 2/3 down the duct, or I believe the UFC calls for 3/4 of the way down the duct, but it can be helpful to not have a single device downstream of the sensor because that may unnecessarily drive the fan speed. If you have major duct splits, so if you don't have one single main supply duct, you may need multiple sensors, and you would use the lowest signal to control to make sure that you're keeping the zones happy. So now we're down in the zone distribution, and even though that schematically there's a lot being represented here, we can recognize this as a pressure independent VAV box, and I circled the flow reading here because that's really the clue that we're not looking at a pressure dependent box, but that we have these pressure pickups that can be translated into flow and are fed to the DDC controller so that it can modulate the damper and maintain constant flow. So this is what that might look like where you have a local zone controller, typically a configurable controller with limited options. But if it's pressure independent, it's picking up pressure readings, also picking up zone temperature and set point readings going to the controller, which is then outputting valve commands and damper commands to maintain the flow and the discharge air temperature being called for. So pressure independent boxes are able to do this regardless of any pressure changes in the system or at the box. They're using some type of airflow measurement or pressure pickup to accomplish this. And based on inputs from the thermostat, we'll select a flow set point that will drive some PID loop command. So let's look at the types of VAV boxes. You can have cooling only, which is the simplest. More common is this VAV reheat type, with one of the drawbacks being is that if you have a lot of nighttime or unoccupied runs to keep some minimum space temperature, then you're having to run your entire air handling unit. Where you have something like a parallel fan powered box, you're able to recirculate air locally to be your first stage of heating, or you could have a series fan powered box which would run with your air handling unit. So here's the control logic blocks for this particular VAV box. So this is the simplest where you have cooling only. And you can see a few things going on here. On the top you have that enable sequence, and what this is saying is that either your system occupancy is not in unoccupied mode, or you're getting a local hardware command from something like a zone thermostat push button that is telling your system to go occupied. So either one of those is enough to enable this PID loop, which would then look at your VAV supply air flow and compare that to, based on your zone temperature deviation from set point, there's some sliding scale for what this box would determine is its flow set point, and then that would drive a VAV damper command. Otherwise, it would go to minimum. You might see sequencing for things like VAV boxes where you have different modes change the set points associated with that system. So here we can look at the left at occupied and at the right at unoccupied, and how flow and coil valve position change. So on the top here we can see that as we change zone temperature set point deviation, we can see the flow changing from a minimum flow in this deadband region where you have ventilation air only coming in towards a max flow cooling as the temperature deviation starts to rise. As it falls and you enter into heating mode, this particular system has a single heating flow associated with that mode. At the bottom you have the reheat valve position, and as you would hope, you have the reheat valve closed as you're in cooling mode and in that deadband. But as it gets colder, you start sliding towards more and more of that reheat valve position open. On the right, when you're unoccupied, this system has a fixed flow associated with that mode, and the same reheat coil valve percentage profile as in occupied mode. So some closing thoughts on VAV box control. So always go with pressure independent boxes if you're looking at new systems or if you're at the design stage. They're not difficult to get, and most manufacturers, I think you'll find, have a lot of that functionality really built in by default to their units. If you're trying to do some resets, as we'll learn, we need zone information to be passed to the plant controllers. So you might want to make sure you get a controller where you have a VAV damper or VAV valve command that you can share with the plant over your control network. And there's certain considerations like zone scheduling if you have dissimilar spaces that you may want to consider building into your VAV box control. So let's finish up with Economizer control. So you can probably guess here based on the damper arrangement that we're looking at mixed air damper command control. So one thing to note is that here we have the return air as a normally open failing actuator, to where the outside air and the exhaust air will take the same control signal, but they will have a normally closed configuration. So we talked in the airside system about how we wouldn't want the same economizer high limit lockout for different climates. That's really specific to the building that you're at and the return air conditions that you're expecting. So there's been some direction from industry, and we can see from ASHRAE, we have these tables that by ASHRAE climate zone give some ballpark numbers about where that economizer high limit may need to be. And this came originally from an ASHRAE journal paper that indicated what types of economizer control strategies were really beneficial to different zones and how enthalpy-based control can end up causing a lot of problems. So if you want to use some of these ballpark numbers, you can find your climate zone from maps like these and plug that into where we have the economizer high limit set point there. But one of the things that the Unified Facility Criteria indicates we should be doing is using our local weather to not just use a ballpark, but use a more strategic number to determine, based on our specific weather bin data, what that lockout or threshold number should be. So we're going to run through what that looks like, first narratively and then on the site chart. So the first thing that we would do is establish our return error condition and run up a line of constant enthalpy. Next, for each weather bin data point, we would plot the dry bulb and the mean coincident wet bulb. Once we have a profile for all those points, we would draw a vertical line where our weather profile meets our constant enthalpy for return error, and draw a line down, and then that would be our economizer high limit for that particular location. So here's what that looks like, a little bit slower. So we start with this return error condition that we would expect. In this case, it was assumed that return error would come back at 78 degrees and 50% relative humidity. A constant enthalpy line is drawn up here, and then the next step would be to plot as much of that weather data as we could around that state, see where they intersect, and then run a line down. So when you read that out, that shows in this case that the economizer high limit set point should be 71 degrees. So there's a slightly modified version of this discussed in the UFC, and it brings in return error. So we're going to kind of take a look at what that is doing. So we follow the same process using our weather bin data, but we have an additional step where we want to note the difference. So how many degrees delta is there between our return error condition and where we ended up selecting our economizer high limit. So in this case, we register that as 7 degrees Fahrenheit. And the reason that we track that economizer difference set point is that as the return error condition moves, because we really just used a design assumption that we're going to be at that 78, but possibly there could be conditions where the return error comes back lower. So as it comes lower, we're able to kind of shift that economizer lockout point a little bit lower so that we're not missing out on being able to use cooler air. And vice versa, as return error gets warmer, we can shut off our economizer earlier so we're not using the more energy intensive air at our cooling coil. So as we've said a few times now, there's a lot of modes of failure associated with economizer. Some of it can be control related, some of it can be mechanical in nature, sometimes it's a combination, but this is going to be a device that you're going to want to pay extra attention to in any type of recommissioning assessment environment. So with that, we're going to move on to some of our other HVAC sequences of operations, such as duct static pressure reset, hydronic pump control, and some of the other reset variables that we could look at.